Post. Ah, I think Mohsen got it. Um, so Raj is a senior research scientist at Google Research in Sydney, Australia, which is where he's joining us from today, I assume. And at Google, he focuses mainly on efficiency and multilinguality, and for Gemini, working I think mostly on post training, or he can clarify. And he additionally has adjunct faculty appointment at IIT Madras, which is where I presume the work that he's discussing today is from. And he previously worked for a long time as a researcher at NICT in Tokyo on machine and speech translation, efficiency, low resource languages, especially Indic and Creole languages and dialect. He also, I must add, it has a certain degree of Twitter fame. But yeah, join me in welcoming him and Raj. We look forward to your talk.
Hey, thanks, Lucas. Thanks for having me, and thanks for the very kind, warm introduction. So I'll just begin with the title of my talk. It's very simple: Romanization and LLMs. I'll get to what the aspects of romanization that I'll be talking about in my talk will be in a bit. But yes, as Lucas mentioned, I'm from Google Research. Um, and just to give you a bit more of a detail about where I'm coming from. So yes, since last year I've been at Google, and I'm also in parallel having an external affiliation at IIT Madras as an adjunct faculty, where I mentor masters, PhD students, and also researchers who want to work on Indic language translation. As you know, that in IIT Madras we have a lot of Indian language focus, but we also focus on other languages which are non-Indic, like Japanese, English, French, from time to time. Um, I was for a short period of time visiting assistant professor at IIT Bombay. Prior to that, I was a researcher at NICT Japan, where I started out with multilingual research, but then went into the directions of efficiency, document translation, speech translation. It just as my experience grew, I was able to focus on many interesting niches and different types of ideas. I'll talk about these things in the next slide just to give you an overview of the body of research that I've done. I did my PhD at Kyoto University, where I was a mixed scholar. And before that, I was in IIT Bombay for my master's. And my thesis advisor was the late Professor Pushpak Bhattacharya, who passed away last year. So, what kind of research I've done? So it spans across some Indic, non-Indic, Creoles. It spans large language models, a lot of benchmarking, surprising a lot of benchmarking work, and architectures. So when it comes to Indic stuff, I have contributed quite a bit to Indic trans models, to Indic BART, document level data sets like Pralekha, speech translation data sets and models like Bhashanuvad. We have an upcoming Indic BERT v3, which hopefully will drop in the next few weeks. It has been delayed due to lack of compute, and also a lot of monolingual pre-training data for Indic LLMs. I worked a lot on Southeast Asian languages like Khmer, and I've also worked on South African languages, which come from the Nguni language families. I've worked with students who've done pre-training as well as post-training. Um, I actually, one of the things that I really was happy working on was Creoles. Now, Creoles are these languages which are inherited from certain colonial languages. And there's Mauritian Creole, there's Haitian Creole. There's so many Creoles. These are minority languages for the most part. And I was one of the few people who actually started the computational body of work on Creoles at the scale of ACL and so on, having being fortunate to collaborate with some really amazing people from Copenhagen University and around the world. Um, about 2021, 2022, I started working on LLMs, where I started, contributing to work such as Airavat, Roman Setu. Roman Setu is what I'll be talking about. One of the things I'll be talking about today. Some translationese studies, the impact of translationese in pre-training, and so on and so forth. I've done quite a bit of work on benchmarks, contribution in some case, manually created in some other cases. Some of these are CVQA, which is a culture-specific visual question answering benchmark, World Cuisines, which is a more niche version focusing on food, Riddle Bench, a benchmark for assessing reasoning capabilities of models for riddle like questions. And then one of my favorite things is architectures, where I focused on efficiency. I want to kind of like ensure that architectures, uh, the models are as small as possible. They can handle low resource languages as well as possible, and they can be inferenced as efficiently as possible. So that kind of should give you an idea of where I'm coming from. So during the Q&A, maybe it's related to the talk that I do, but if not, if you have any questions on these topics, yeah, feel free to ask me anything during the Q&A and the interaction session. So in this talk, I'll be talking about romanization in LLMs. This will be handled in two parts. In the first part, I'll be talking about early investigations on using romanized representations in LLMs. It was just random curiosity, which led to some exciting findings, and it had some efficiency implications. The second part is where we, once I'll take the conclusions of part one, and I'll talk about how we further investigated LLMs from interpretability perspectives to understand when and where romanization pops up and what role it might play in the overall language capability development in LLMs. So the first part was a simple curiosity. And back 2 years ago, 2.5 to 3 years ago, when Llama 2 dropped, these Llama models, right, they were not very good at supporting Indic languages because the tokenizer was mainly English centric. They could support a small amount of Indic languages. They could support Hindi, but not at all. But this meant that if you wanted to do some so if you wanted to perform some classification tasks for non-English scripts or non-Latin scripts, you could do pretty well. But when you wanted to generate in non-Latin scripts, you would end up paying a lot of token tax. It was quite painful, and we couldn't get anything done. So our question was, how can we extend the capabilities of LLMs to the languages written in non-Latin scripts? Now in 2026, that is not as much of a problem, but where we started, it could be a bit of a problem. And some of these things still have implications even today. So what I realized is when I gave Llama a sentence written in Devanagari script for Hindi, um, it could understand this sentence, but then I was curious, what if I just converted it to a Roman equivalent from Devanagari script to the Latin script by transliterating? I was curious whether Llama could understand it or not. And when I prompted Llama 2 with this romanized version of the Devanagari sentence, it could continue generating in this romanized form. So I was like, hold on, this model probably has the capability to understand, let's say, non-Latin scripts written in Latin form. And that got me thinking, is there something internal to the model or to the tokenization that will allow me to handle non-Latin script languages, but in Latin script? And that is where our work Roman Setu came into the picture, where we tried to use romanization as a bridge. So some research questions we had is there an efficiency gain through romanization? If so, which approach to romanization is the most efficient? Do romanized inputs lead to embeddings that are better aligned to English representations as compared to native inputs? And does romanization improve downstream task performance across multiple NLP tasks? Our main concern was the third question. We just wanted to know if romanization would improve performance or not, especially given that the tokenizers didn't really support non-Latin script languages. So what is romanization? It is transliteration, converting text from one script to another. And romanization only focuses on transliteration into Roman script or the Latin alphabet. So if you have the Ukrainian word privyet, you would romanize it as this particular word privyet. In Hindi, if you have the word fool, which means flower, you would romanize it as PHOOL. Of course, romanization is non-standard most of the time. So it could become PHUL, it could become anything. But for the purposes of this work, we didn't really care about it. We just standardized to one specific thing that our transliteration models could handle. And then what we did was for every language, Indic language that we were interested in, we were interested in 5 languages: Gujarati, Hindi, Malayalam, Marathi, and Tamil. What we did is we tokenized the words in a fixed corpus, and we computed fertility. So fertility gives you the average number of subwords a particular word in a language is segmented into. So when we gave in Gujarati corpus and got its fertility, we got the fertility to be 18.44 if we use the Gujarati script. For Hindi, it was 7.36, and so on and so forth. So it means that per word, that we wanted to tokenize using subword mechanisms, we'd end up with at least 7.36 subwords. Whereas in English, the fertility was close to less than 2. So that means we'd end up decoding for 3 to 4 times more, sometimes 6 times more, uh, in order to get a single word being decoded. And that's very painful. And these are average numbers. Try to imagine what would happen if you considered words of varying lengths. It would just be too much. The sequence lengths were off the charts, and we often had truncated generations, which is a pain. However, if we Romanized these scripts and then got them tokenized and then got the fertilities dropped down substantially. We went from 18.44 for Gujarati to 3.39, for Hindi from 7.36 to 2.98. This was the Indic transliteration toolkit based romanization. There are some other rule based transliteration or romanization methods which we also used, but those led to higher fertilities because those were rule based, and so there were a lot of non-standard transliteration rules which didn't work out well. But the key story over here is that the token tax that was imposed on native scripts is no longer imposed when you convert them into Roman scripts. That's well and good, but can the model really, even though you've reduced the fertility, even if you've reduced the token tax, can these models even do well even if you convert them into Romanized versions? Because how much has the model seen in terms of Romanized content? That is also a concern. And if the model hasn't seen much, it's not going to perform well, is it? So that's what we looked into next. So the way we created the bridge is we have native script data, which means whatever Indic language is written in the original native scripts, we converted it into Romanized format via transliteration. Then we had some equivalent English data. And what we did is we combined all of this data. We took a base LLM like Llama 2 in our case. We did some continual pre-training. And then we had some English SFT data, which we translated and romanized into the target languages for post-training. We did instruction tuning, and we got a fine-tuned model. And this fine-tuned model we finally used to benchmark on various downstream tasks. We had various settings like where we did SFT with only native script, SFT with only Romanized script, SFT with native plus Romanized. You can look at the paper for this, but I want to get to the key essence of what our investigations were. So as I earlier mentioned, our languages of focus were Tamil, Malayalam, Hindi, Gujarati, and Marathi script. So you can see that there's 4 different types of scripts over here, Marathi and Hindi sharing the same Devanagari script. So I'll go into details about what these transliteration schemes are, continual pre-training, instruction fine-tuning, and evaluation steps. So for transliteration, we use the Indic XLIT library or toolkit. This is a model that was developed at IIT Madras at AIF Bharat. It still is, I believe, one of the state-of-the-art transliteration schemes for Indic languages. At least the romanization quality was pretty good. And it was also the only model that gave the least fertilities for all the Romanized texts. For continual pre-training, what we did was we took 500 million words per language and we Romanized them and we combined them with 500 million words of English. So when we say 500 million words, it means we actually took word counts because these are all space separated languages. So it was very easy to count these words, not a problem. If it were non-space separated languages like Japanese or Chinese, we'd have to rely on some kind of pre-tokenization to do this counting. Counting the number of tokens and words is always something that needs to be taken with a pinch of salt because it really is language dependent and sometimes you need to make plus minus adjustments to these things. Note that the data that we used was document level data and the models that we trained already had some concept of romanization. Like Llama 2 already had some concept of romanization. I don't know if Llama 1 had that capability, but we didn't try because Llama 2 was just better at that point of time. And one key point over here is we included English data because we wanted to avoid catastrophic forgetting in the process of introducing Romanized as well as native script capabilities. We also did not do any vocabulary expansion because vocabulary expansion is another nightmare in itself. I have another paper on vocabulary expansion, and we showed how we can do some very cheap and efficient vocabulary expansion and still retain capabilities. You can read about it if you go on my Google Scholar. Now, when it comes to instruction fine-tuning, what we took was we took FLAN, which consists of 65K training instances and Dolly 15K training instances. We translated them into 5 languages. We also have machine translation data for English to XX for the 5 languages and XX to English for those 5 languages, we took only 20K sentences per languages, and we romanized all of this. And then our final mixture was the native script data, we have the romanized script data, and we have the original English data also. So we just do a number of settings. We tried on a variety of settings in order to ensure that our model had the capability to handle all types of scripts, and our main priority was to assess whether romanized inputs and outputs had the best performance or not. But if we could also improve native script generations, then it kind of hinted that we have the ability to transfer English capabilities to native script capabilities via the romanized equivalents as a bridge. So for the evaluation, let me go over this table one step at a time, right? So looking at the columns, we have the base LLM evaluation, which we evaluated in 1-shot and 3-shot mode. Then we took the continually pre-trained model, evaluated it in 1-shot and 3-shot mode, and then the instruction fine-tune or the post-trained model, which we evaluate only in 0-shot mode. Now, for what is the input? We have the input in native script format, which is denoted by N, and the input in romanized script format, which is denoted by R. One thing you have to keep in mind is all our final evaluations, the inputs may be in native script or romanized script, but our final evaluations are always in the target native script. So in other words, if the output of our model is in romanized form, we convert that romanized output back into native script representations, and then and only then compute the final evaluation scores. We do not evaluate, at least in this table, I'm not showing you any scores of any kind of romanized script evaluation, because those would lead to slightly inflated numbers, and that's not good. So one thing to note is looking at the machine translation use cases. Let's focus on English to XX translation, because XX to English translation means that the model has to deal with natural language understanding. But EN to XX involves understanding as well as generation, where it has to generate XX, not understand XX. So this is where our CPT and our post-training really helped. So if you took a look at the base models, right? If you give the input in native script, or if you give the input in native script, regardless of the number of shots, your performance is pretty abysmal. These are CHRF scores, and the performance is pretty bad. 14 CHRF score is really nothing. You can't get any kind of translation quality. The outputs were mostly gibberish, a lot of truncations and so on. On the other hand, what would happen if you did continual pre-training with romanized as well as native script data, you can see that the native script performance improved quite a bit. So if you ask the model to produce native script translations directly, you would get an improved performance over the baseline model, which really wasn't trained for native script generation. But the translation quality for generating in romanized script is much higher than the quality for generating in native script, which shows that we've reduced the token tax and also improved the model's capability to handle generation in a specific language via romanization, which once you back transliterate into the native script, still manages to retain the performance, which is a good thing. And what happens when you do post-training? Well, the performance, the numbers in general go up, but the gap between native script generation and romanized script generation capabilities just shoots up. We have translation, the CHRF scores of 37.40 for native script generation, but if you have romanized script generation followed by transliteration back into the native script, the performance jumps up to as high as 46.87, averaged across 5 languages. We see similar trends in Excel sum, which is summarization, and for headline generation for Indic languages. So it's very clear that for these models, which really didn't support a specific language, you could have a fallback on romanized representations, and then you could back transliterate into the native language, but you'd still have this amazing gain in performance in different languages. So that is one of the cool findings that we had, and it was consistent across various tasks. I'm only showing like 3 to 4 tasks over here, but there's a lot more in the paper that we evaluated on. So what is the big picture? The big picture is that overall by task, our instruction fine-tuned and Romanized representation models outperform native script representation models across a variety of tasks. And by language also, we saw there was a consistent gain over simply taking a base model or a CPT model. Instruction fine-tuning really helped us extract the juice in terms of how much impact romanization can have for models which inherently do not have native script representations for extremely low resource languages. So how this, I just want to highlight how our work was different from previous works. So there were some previous works focusing on transliterations, but the key difference is the previous work focused on multilingual language models, whereas our work is focused on English heavy language models. So we are actually working in a more dire situation. Previous works focused on encoder only models, whereas we focused on decoder only models, also generalizable to encoder decoder models. Previous works did a lot of vocab expansion, whereas we didn't do any vocab expansion. We had to make do with whatever we had. And previous works did NLU only. We did NLG as well as NLU, as evidenced by our work on indicate stream, which are understanding benchmarks. So yes, we showed that romanization can bridge the gap between English heavy LLMs and native representations and boost everything pretty nicely. And I'd like to take us, sorry, one thing is I'd like to highlight some limitations, and I think this might be something you've already noticed, is transliteration involves a lot of errors and losses, especially when you back transliterate into original scripts. So one thing we noticed is when we looked at the romanized outputs that we got from the model versus the back transliterated outputs, the romanized outputs were a true indicator of the actual performance, whereas the back transliterated outputs, because of transliteration errors, they actually tended to give a lower bound of the, or they tended to underreport or underestimate the actual capabilities. So even though our CHRF scores looked like 47, it actually should be as high as 50, because that number, because of back transliteration issues, we got like, you know, a bit of reduced scores. However, I can say that if our transliteration schemes get perfected, we'll end up getting better performance. You'll be able to bridge, you will be able to reach that ceiling performance and report it clearly as well. So I'd like to take a break over here in case anybody has any questions or anything on their mind. Okay, no problem. Let's move on. So now that we know that romanization has played a role in the model's internal capabilities, the key question is when and where, and what exactly is that specific role uh, doing? Why is it that the model is able to understand both romanized as well as native script representations? And for that purpose, we did a bit of interpretability studies. So language model interpretability is this amazing tool. I know that Lucas has also worked quite a bit on model interpretability, logit lens, and routing interventions, and so on. So if you're aware of his work, then this might also be interesting to you. So our hypothesis was that LLMs leverage Romanized forms of non-Roman script languages in the hidden layers when processing non-Roman script languages. What does that mean? For that, we need to understand what the logit lens approach is. And to be specific, you know that in the transformer model, you process one token at a time during inferencing. And then suppose the sentence is so long and thanks for all the fishes, right? Now, when the word for is given as the input to the model, it goes through a bunch of transformer layers. And then at the final softmax layer, we do unembedding, and then we get the softmax. Now, we usually train models to apply this softmax on unembedding basically only at the the final layer of the model. But logit lens allows us to simply take the softmax layer and apply it to the hidden representations at any intermediate layers and see what the logits look like. Of course, this is not designed to handle all layers. We can train it specifically, but even without training, we get some kind of interesting insights. It allows us to know what the distribution of tokens look like at intermediate layers, not just at the final layers. It's a very simple but very powerful technique. And there has been previous works on finding English biases in LLMs. So previous works have shown that LLMs generalize via language agnostic concept towards English. So for example, whenever you give an input, right, as in Chinese, what would happen is before the final layers produce Chinese tokens, the pre-final layers often have Romanized script generation or Latin script generation in the intermediate stages. In other words, the model understands a lot more of Latin script or Latin tokens during the intermediate stages. It tends to produce these tokens at intermediate stages if you use logit lens. But when you reach the final layer, the model finally decides, yes, I need to generate in Chinese. So the distribution shift towards Chinese tokens. So our hypothesis is LLMs leverage Romanized forms of non-Roman script languages as an intermediate bridge. Specifically, we call this latent romanization. And what we mean by that is that before the tokens are generated in their native script format, the intermediate layers see their Romanized formats first. So for this purpose, we took Gemma 2 9 billion instruction tuned models, Gemma 2 9 billion models without any instruction tuning, Llama 2 7 billion, Llama 2 13 billion, and Mistral 7 billion. We avoided using Llama 3, if I recall correctly, because Llama 3's tokenization was byte pair encoding based, which really prevented us from doing very good analysis of what tokens are being generated via this logit lens. So we skipped that. For the languages, we use Hindi, Tamil, Telugu, Gujarati, Malayalam, Chinese, and Georgian. Our initial focus was mainly on Indic languages, but then for the purposes of doing writing a good paper, we decided to expand into Chinese and Georgian, which are not very related to Indian languages. As before, we used Indic transliteration for Indic languages. We used the pinyin representation. Sorry, there's a typo over there. Pinyin representation for Chinese and Unicode for Georgian. The data sets we used were simple word level data sets, and I'll introduce you the tasks as well. So we had three tasks. The first task is to just predict one word translations. So we would few shot prompt the models to do French to Hindi translation. This is just one of the language directions, but we did it for a variety of languages. So we'd give a 6-shot prompt to translate from French to Hindi. And then we'd given a word like the word for flower and ask the model to produce the Hindi translation. We also have a repetition task where we take the same word in Hindi and ask the model to produce the same word. So it's machli, machli, aam. And finally, we'd given the word for flower, and hopefully the model also produces the word flower. But we are interested in is in the process of generating or repeating the word, what happens in the middle? And then we have the close task where we'd ask the model to fill in the blanks and see whether the model fills in the blanks properly or not. So we'd give some few short examples of what fill in the blanks means and ask the model to generate the same. So the first research question is, do LLMs exhibit latent romanization during multilingual text completion tasks? And this is something that becomes very intriguing. So we consider the word door, which is pronounced as darwaza in Hindi in the Devanagari script, and its Romanized equivalent is darwaza, Darwaza. It's written as it is. And of course, the task was French to Hindi using the 6-shot template that I mentioned before. And we tried to visualize the Romanized representations occurring in the intermediate layers during multilingual tasks. Now, you can see that in the process of generating the token darwaza, as the model is predicting the word darwaza, it's very interesting to see that the word door appears in the intermediate layers. Now, another interesting thing is darwaza, because it is written as ends with the word aza, you can see that the word aza appears in the pre-final layers. So in other words, this is just one example, but we found that the more and more words we analyzed using this approach, we found that the model has a nice tendency to produce the English translations first and then go into the native script translation. But also the romanized equivalents of these particular translations. So in other words, the model has a tendency to produce romanized equivalents of words before going into the native representations of words, which is very intriguing. We scaled up all our observations and we found that this happens quite a bit. So we did an analysis of translation, repetition, and closed tasks, and quantitatively analyzed the last n layers of an LLM. And we defined a latent fraction as the fraction of instances where Romanized tokens occur with a probability of 0.1 across timestamps across a variety of samples. We evaluated for full words, we evaluated for the first subword, and we evaluated for the last subword generation. So we wanted to know how often latent romanization pops up in the process of generating the final token in the native script. And interestingly, for the Indic languages that we focused on, we can see that after the 36th layers, often we saw that the romanized representations of the native script equivalent tended to pop up in the pre-final layers. So between layers 36 to layers 41, before the pre-final layer, romanized representations used to pop up. But then as the model is reaching the final layer, the number of romanized representations would start dropping again in favor of the native script representations. So essentially, the model at this very language agnostic set of layers, which usually is the middle set of layers in any model, it tends to be aligned more to its romanized representations before branching out into the final representations. And as you know, the romanized representations are more aligned to English, which is usually the main central pivot, something that holds all of the languages together, especially in the middle layers. So it kind of makes sense, right? That during generation, it would be English as the backbone, branch off into romanization, and then branch off into the native script representation. Now, interestingly, this does not happen for Chinese. And our hypothesis is that, sorry, did somebody ask a question?
No, I just
Oh, yeah.
said that the findings cool. Sorry.
No, yes, of course. Thank you. There's more to chat about. There's more interesting, cool findings that we have. Just hold on to your seats. So we didn't find this for Chinese, and our hypothesis is because Chinese is one of the, let's say, more higher resource languages in any models. We found out that Chinese doesn't really need to go through this process. It happens at a very small fraction, but not a lot. Now, what happens for the first subword generation versus the final subword generation? We find that it is roughly the same, but the first subword is typically not generated in the romanized format, whereas the last subword is more prone to be generated in the romanized format. So this model sees a hodgepodge of all of these representations, but the closer we get towards the middle layers and the final layers, the model really likes romanized representations of these very low resource languages. That is the conclusion you should take away. This plot shows you the latent romanization frequency, which is measured for last token generation timestamp across tasks, and a romanized token is counted if its probability is greater than 0.1 in the last 10 layers. And we see that a very high latent romanization frequency observed in repetition tasks. So as I mentioned, we have the translation task in blue, the repetition task in orange, and the close task in gray. And you can see that, yes, plenty of the frequency of romanization is pretty high. Interestingly, for Georgian repetition tasks, a massive amount of romanization takes place. I'm not sure why. I don't know if we investigated it or not, but it should be interesting to understand if it is because there is more of a Latin influence on Georgian as compared to on Indic languages, or maybe it's a function of the data in the pre-training mixture, whatever. We are not sure, but it is something that pops up if enough to know that this is a trend. So this brings us to our second research question. How does the representation of semantic concepts in LMs compare between native and Romanized scripts of non-Roman languages? And for this, we went to another mechanistic interpretability tool, which is called as activation patching. Now in activation patching, now by the way, activation patching is a really cool thing. What you do is you take a you essentially prompt a model in the forward pass and save the hidden representations. You now take these hidden representations and put them in the place of a forward pass of another, let's say, prompt. and you try to see if these activations now influence the final generation in some other prompt case or not. So this was invented by Dumas et al. 2024. I'll give you a much more better explanation. So now consider that you are translating elephant into, you want to patch source prompts translating elephant into target prompts translating sun. So now suppose you have, you want to translate the word elephant, right? So you have the model, you give it a prompt, a one-shot prompt saying in German, the word is this, and then the Italian word is this. So you give it one-shot prompt, and then in German, you give the word elephant. Now, before the Italian word is generated, you take the activation corresponding to the subword for the German word, which is ANT, and then you save this. Now, on the target side, suppose you're translating from French to Hindi, you give a one-shot prompt. Now, before, in the normal case, what you do is you'd prompt the French word, and then you'd ask the model to produce the Hindi translation, right? But instead of using the activation corresponding to the last subword in French, you take in the activation for the last subword for some other prompt that you had already computed forward, the forward pass for. And you want to see the influence that this activation patching has. Now, interestingly, if you let the model go on as it is, then it would generate the natural translation in Hindi. But because you patched in the activations for translation of something into of the word elephant in German, you end up getting the model to produce the word for elephant in Hindi. So although the input French word is not elephant, the output distribution contains an overwhelming probability allocated to the generation of the word elephant. And it's not just in Hindi, but it also is in Italian. So it's very interesting that the probability distribution is not only biased toward generating the word elephant for Hindi, but also takes in the behavior of generating the word elephant in Italian, despite our task being French to Hindi translation. So what we wanted to do is, we wanted to know if by patching in the activations for romanized generation, can we still end up getting the correct translation in native generation or not? So what we do is we take the representations patched in from source prompt with input language in the romanized versus in the native script. So what we do is Hindi to Italian versus Hindi romanized to Italian source prompts. And then we patch this into Malayalam to Italian target prompts. So what we can do is we take Hindi to Italian as a task, we take the activations, and then we patch it in for Malayalam to Italian prompts. And we want to see if switching the native script representation of Hindi to Romanized script representation, whether it has any kind of negative effect or not. And interestingly, it turns out that you can safely switch out native script representations for Hindi with the Romanized script representations, take the activations from intermediate layers, patch them into the model, and the model still behaves very normally, and it has the same exact effect, or more or less the same effect in the generations. So what are the differences in hidden layer representations when processing the same language and Romanized and native scripts? Well, take this particular case of French to Malayalam in Romanized format versus French to Malayalam direct generation. So what happens is that when you try to do French to Malayalam in the Romanized format, you, as per our initial, logit lens investigation, we found out that the model tends to produce the word "pu," which is the word of, which is the first subword of the word pushpam for Malayalam. Whereas when you do French to Malayalam native script generation, it generates that particular subword. So this is okay. And then we wanted to compare translations for Romanized versus native script. So the translation task was evaluated with target text in native and Romanized scripts. And we focus only on the first token generation, including synonyms. And the probability is computed by summing over all possible tokens for the target language. And interestingly, we found out that the Roman script representations emerge 1 to 2 layers earlier than native script counterparts. And this is very consistent, right? Why does this happen? It is not very clear, but it is very likely because of the model's training being overwhelmingly in English and Romanized representations having much more alignment to English representations or native English representations. So just to highlight is that if you do French to Malayalam generation in Romanized format versus French to Malayalam generation in native format, you will see that the Romanized representations pop up a lot earlier, whereas the native script representations just pop up in the final layers. So it means that there is a lot more of latent romanization in the models that takes place if you make the model produce content in the Romanized representation. So the conclusion is that romanization acts as a bridge between the concept space and the language-specific region for non-Roman script languages. The semantic concepts are encoded similarly across native and Romanized inputs, which indicates a shared internal representation. And this is what I really want to highlight over here, that at the middle layers of a transformer, there's a lot of language sharing, a lot of representation sharing that takes place. But it seems that the Roman representation of a given language has a lot more sharing with English as compared to the native representation of a language with English. And when translating into a Romanized script, target representations emerge earlier compared to the translation into native script. So this is also a very important thing. So in other words, it might be worthwhile to understand the relationship between the Romanized script and the English tokens and the Romanized script and the native tokens to understand how we can transfer from English capabilities to native script capabilities via romanization as a bridge. And that is exactly what I consider as some of my future work alongside with enabling models to perform well regardless of romanization. Note that romanization is still an important aspect of code mixing. So we will still need to have romanization capabilities, but I would hope that we use romanization as a bridge to transfer capabilities rather than simply get the models to produce stuff in romanization. Now, one thing is, what if we encourage romanized representations to emerge in the model earlier or later? Will that have a positive effect on transfer learning? I'm not sure. It's probably worth a try. Maybe somebody's already tried it. And one other curiosity is that we've done this for text-only models, but what about multimodal models, right? Suppose we have a vision language model which can process OCR content in English, OCR content in Hindi, blah, blah, blah. Now, do these models have some kind of latent alignment between representations of vision tokens in different languages? And it would be very interesting to apply some interpretability techniques to see what kind of latent alignment takes place for these kind of multimodal models. So this is it. I just wanted to give a quick shout out to my collaborators at IIT Madras and IIFA Bharat and IIT Bombay for all of this fun work that I've been a part of. And that is time. I'm happy to take any questions.
Hi, yeah. Oh, sorry.
Go ahead.
Okay, thank you. First, I want to say thank you. This is fascinating work. Thank you for sharing with us. I have one question about, can we dig more deep into why this finding, why do you think is the underlying mechanism for the conclusion that Roman representation of, for example, Hindi are more similar with English, like aligned with English in the middle layers?
Okay, so I have only hypothesis. I can only offer hypothesis here. I cannot give you strong conclusions because I would really need to back that up with experiments. But based on my experience, I can say, so think about it this way, right? A lot of pre-training data. So I don't know how much you've been on the Indian side of the internet, but India being a very multilingual country, we have the tendency to mix in English along with a lot of our native word usage. So often you'll see websites with a lot of romanized content in it. You'll see people writing something in their native language, and then in the brackets, you'll have some indications of what the translation in English is. Because, not everybody will understand the native word for certain things. So then giving the translations or transliterations in the bracket,
Mhm.
that is quite a bit of the data that happens in the Indic context. Social media in India is just a hodgepodge of romanized content and native script content and people just interleaving words in different languages that happen. So my hypothesis or my guess is that this is an artifact of how the training data is. And because Indic data does have an overwhelming amount of code mixing and mixed writing, it is just something that arises from that. The model during training just learns to say like, oh, somebody has written the word khana in the native script, but then in another context, in a similar but related context, they have used the word khana in some kind of code mixing writing. And the model is probably just, it's these big models, they have their own internal representation learning. It just probably pops up at that. This is just my hypothesis. I cannot give you a concrete answer for
Yeah.
this. I'm so sorry.
No, thank you. This exactly is like I had the same hypothesis when you're talking about this. So I completely agree. And I also think this actually kind of explains why in Chinese we don't see the same finding because in Chinese I think there's rarely any code switching between pinyin and the characters. So that
Yes.
might be another reason why we didn't see the same finding.
Yes. Interestingly, by the way, we can see more evidence of this happening in Japanese
Mm-hmm.
because in
Yeah,
Japanese, there's a lot of English loan words that are taken in. Sometimes people write this directly in Roman script. Sometimes people write this in the katakana script. Um,
right.
so in some of our investigations, we saw small evidences for this Romanized latent representations popping up for Japanese, but it's not as much as it happens for Indian languages. So I imagine you could probably do a study where you do a corpus analysis where you find out which languages are more prone to Romanized content in them, and then do a correlation with how often Romanization appears during the intermediate stages. And there might be some kind of one-to-one correlation of how often this happens. It might be an artifact of the data and the culture itself.
Right. So this actually says something about the phenomenon of code mixing or code switching in different
Yes,
cultures.
yes,
Fascinating.
yes,
Thank
yes.
you.
Yeah, and my question was about so we discussed Indian languages, we discussed Chinese language, but I guess I'm curious about Georgian, which might have been the first work and not the second work in which you included Georgian. So if so, that maybe there's not results about it. But say something like Georgian, where it's very rarely written in Latin scripts, or I don't know, I would assume because there isn't maybe the same code switching phenomenon as there is in India. Um, and so then I would imagine that the latent representations aren't going to be as often in like in Latin words. Maybe it just directly goes to English, the internal representations. I don't know.
Yes.
Maybe you have thoughts on what would
Yes,
happen
yes, yes,
for
yes,
language like
exactly,
that.
exactly. So for Georgian, this was indeed the case that we did not see an overwhelming amount of Romanization taking place as we did for Indic languages. And this again just goes to highlight that this is an artifact of just how people write in specific languages. Um, it, I guess, yeah, I don't recall the exact result that we had for Georgian, but as far as I remember, we saw less of an overwhelming evidence for Georgian as compared to Indian languages, but it was a lot more than for Chinese. Like Chinese definitely had the least amount of latent Romanized representations popping up. Georgian had a bit more, but Indics just had an overwhelming amount.
And then the second question I have is related to thinking. So now that a lot of LLMs are producing thinking tokens, um, like this kind of is another dimension. It's not latent because they're actually generating tokens. But for a lot of these lower resource languages, like the defaults to thinking in English, and they're I guess say if it's Hindi prompts or whatever and thinking in English, what do you expect? Say the latent, like if we applied logit lens to the thinking tokens. Do you expect it to just be in English?
Right. So I think the latent, when you apply logit lens and get these latent tokens, I don't think the behavior will particularly change just because it's a thinking model or a non-thinking model. Because thinking is just a capability that you have encouraged, but it's just token generation. It just produces extra tokens, does some kind of chain of thought reasoning. I don't think simply training the model to be a thinking model will have any specific impact on the latent romanization. Latent romanization will likely pop up no matter what you do. I think it doesn't have anything specific to do with thinking. Maybe your finding is different. Have you tried anything on thinking models versus non-thinking models? I'm very curious about it. Kind of opening up the stage for discussion right now.
I haven't looked at, like, say, the
Okay.
internals during thinking.
Okay. But I
Maybe
can
somebody
say
has something.
this, that we do have a work which is actually going to be uh, it's going to be presented at EACL, which is about, can you take existing, let's say, reasoning models, which have an overwhelming tendency to think in English, even if your prompts are in, let's say, non-English languages. And if you force the model thinking to be in a specific language by some kind of language agnostic prefixes or something, do the model's capabilities go up or go down, or do they remain the same? And we found out that for models like Quen, the model tends to retain most of its performance, even though it does reasoning purely in the target language. So you can actually force the model to reason in a specific language. It can do pretty well. I feel like modern language models have bridged a lot of the language gap in terms of token generation capabilities. It is able to reason in effectively any language despite any training. I'm not sure why that is happening. Maybe it's because of just a lot of parameters and a lot of good post training. But I can certainly imagine, if you force the model, if you take a, let's say, model that default thinks in English, and then you switch you do latent, you do some kind of logit lens analysis on, let's say, the thinking tokens, to see if the thinking tokens produce representations for the language of the prompt, we might see something. Alternatively, if you force the model to think in the language of the prompt, do this logit lens analysis, does it produce these kind of romanized equivalents before producing the final target language tokens? It's a bit of a curiosity. I would say that it's going to be an overwhelming amount of effort, because you can just end up generating 4K thinking tokens, and whether doing logit lens analysis for 4K tokens makes sense or not is kind of a question. But yeah, I think definitely if you got the compute and the time for it, and you can run something in the background, it's probably a nice extension to this particular direction.